we're going to be graphing a problem. So say we have our function g at x equals x squared plus 1 over 4x squared minus 9. Our first step is finding our x-intercepts. So 0 equals x squared plus 1 equals 4x squared minus 9. We have 0 equal x squared plus 1. Negative 1 equal x squared. This is not possible. Therefore, we have no x-intercepts. How about our y-intercepts? We can sub in 0 for x, so y equals 0 squared plus 1 over 4 times 0 squared minus 9. And this will give us, this is 0, that gives us negative 1 over 9. So we already have a point on our graph, which is our y-intercept, which is negative 1 over 9. Okay, so step 3, we need to find our vertical asymptote. So our vertical asymptote is when our denominator equals 0. So 9 equals 4x squared, 9 over 4 equals x squared, square root both sides, x equals plus or minus negative 3 over 2. Then we need to find the behavior of the function as it approaches our vertical asymptote. So we need to draw our interval table. First, we're going to find as x approaches negative 3 over 2 from the negative side, x approaches negative 3 over 2 from the positive side, x approaches 3 over 2 from the negative side, and then x approaches 3 over 2 from the positive side. On the top here, we just have our function and then its behavior. So for here, you can use the point negative 1.5001. Here you can use negative 1.4999. Here we can use 1.4999 and then 1.5001. So if you take these numbers and plug them back into our function, you will find that as x approaches negative 3 over 2 from the negative side, function's positive. As it approaches it from the positive side, function's negative. And then same thing for these ones, it's negative and positive. So for here, since it's positive, it approaches positive infinity. Since it's negative, it approaches negative infinity. And then same thing for the other two. Therefore, as x approaches negative 3 over 2 from the negative side, b prime x is going to be infinity. As it approaches it from the positive side, it's going to be negative infinity. As it approaches 3 over 2 from the negative side, it's going to be negative infinity. And then as it approaches it from the positive side, it's going to be positive infinity. Okay, now we're going to look at our horizontal asymptote. Now we know if the exponents are the same, we divide the leading coefficients. So our exponents are the same. Our leading coefficients are 1 over 4. Therefore, our horizontal asymptote is y equals 1 over 4. And we can box that. Then we need to find the behavior as our function approaches the horizontal asymptote. So we're going to pick x equals 1000. And if you plug that into our function, you'll get 0.2500008. And if you get g equals negative 1000, you get 0.2500008. And both of these are greater than 1 over 4. So what that tells us is as x approaches positive and negative infinity, so the 1000 and the negative 1000, the function is above Since it's greater, it's going to be above the horizontal asymptote, which is y equals 1 over 4. Step 7, we're going to do the first derivative test. So we're going to get the derivative of this function. Then we're going to let our g prime at x equals 0 so that we can find our critical numbers. So our 0 is just going to be equal negative 26x. Therefore, our g prime at x is going to equal 0 at x equals 0. And also, we're going to find where our g prime at x does not exist. It's going to be when our denominator equals 0. So 0 equals 4x squared minus 9. And as you can tell, here it does not exist at positive and negative 3 over 2, which was our vertical asymptote. However, we're still going to include this as one of our critical numbers. So our critical numbers So our 8th step, we're going to draw an interval table. So we have g prime at x and then just g at x. Now if we recall, our critical numbers were 0, negative 1.5, and 1.5. So we're going to go negative infinity, negative 1.5. And we know that one of our points, our critical numbers, is 1.5. Then we're going to go negative 1.5 to 0. 0 is another critical number. Then we go to 0 to 1.5. 1.5 is the critical number. And finally 1.5 to positive infinity. And we know already that at 1.5 and negative 1.5, our function does not exist. And we know that at 0, g prime at x is also 0. So we can pick any point in this interval. We can pick negative 2. If we sub it into our g prime x, it'll give us a positive number. Here we can take negative 1. If we sub it, it'll give us 1. Here we take 1, we'll get negative, and here we can take 2, and we'll get negative. So since it's positive, it's increasing. Here it's increasing. Here it's decreasing, and here it's decreasing. Now, since before 0 it's increasing, so it's going up. Then at 0 it starts decreasing. Then we know this point is our max. So therefore, maximum is going to be at 0. And then if you just want to sub our 0 back into this function so that we know our y value, we're going to get negative 1 over 9. So that's our maximum point. Our increasing interval is going to be between negative infinity to negative 1.5 and negative 1.5 to 0. Our decreasing interval is going to be from 0 to 1.5 and 1.5 to infinity. Okay, so for step number 9, we're going to find our g double prime x so that we can find our points of inflection and we can determine our concavity. so g double prime x, once again, so since we already found our g prime x, we'll find the derivative of that, and we get okay, so for our g double prime x, we got 78 times 4x squared plus 3 divided by 4x squared minus 9 cubed. We're gonna let g double prime x equals 0. So that's just gonna have 0 equals 78 for x squared plus 3. And then 0 equals 4x squared plus 3, negative 3 equal 4x squared, negative 3 over 4 equal x squared. Since you can't square root a negative number, then never. So therefore, our g double prime x equals 0, never. But we have to also check where it does not exist. So it doesn't exist when 0 equals our denominator. And once again, we're gonna get, if we solve, we'll get x equals plus or minus 3 over 2. If you recall, that's again our vertical asymptote. So we'll draw an interval table, g double prime x, and then we have our g at x. So we have negative infinity to negative 3 over 2. We know that negative 3 over 2 does not exist. Then we have negative 3 over 2 to 3 over 2. We also know that 3 over 2 does not exist. And then from 3 over 2 to infinity. So we know here it just does not exist, does not exist, does not exist, does not exist. And if you get a point in this interval and you sub it into our g double prime x, you'll get positive. That means it's concave up. If you get from this interval, it'll be negative, so it's concave down. And then positive and concave up. Therefore, our function is concave up in the intervals negative infinity to negative 3 over 2 and 3 over 2 to infinity. It is concave down between negative 3 over 2 and 3 over 2. So now using all the information we have, we can graph our function. So the first thing is we're gonna draw our horizontal asymptote. So our horizontal asymptote is that y equals 1 over 4. So we can say that if that's 1, that could be approximately 1 over 4. And I just like to do dotted line. Then we're going to draw our vertical asymptote, which we have 2, at x equals 3 over 2 and x equals negative 3 over 2. So this one's x equals 3 over 2, and then x equals negative 3 over 2. The next step is drawing our end behaviors near our vertical and horizontal asymptote. So for horizontal asymptote, as x approaches positive infinity and negative infinity, it's above the horizontal asymptote. So this is our horizontal asymptote, and on both sides it's above. For our vertical asymptote, so as x approaches -3/2 from the negative side, so that's from the left side, it goes to infinity. So that'll be over here. Now as it approaches from the positive side, so as it approaches from the right side, it goes to -infinity. So that'll be over here. As it approaches +3/2 from the negative side, so from the left side, it goes to -infinity again. And finally, as it approaches 3/2 from the positive side, so from the right side, it's going to go to infinity. So that'll be over here. Now we have our asymptotes and our end behaviors. We can draw our y-intercept 0 and -1.9. So 0 and then kind of -1.9. This is a point on our graph. Now, and that is our maximum. So we know that's our maximum. Now our increasing interval, it's increasing from -infinity to -3/2. So -infinity to -3/2, it's increasing. However, is it concave up or is it concave down? Well, we know that -infinity to -3/2 is concave up, so it's gonna look like this. Then I'll just look at the other side. So it's decreasing from 3/2 to infinity. So it's decreasing, and you can kind of tell that already from our end behaviors. And we just need to determine if it's concave up or concave down. So looking here is concave up as well. So we can draw it just like this. And then from -3/2 to 0, so that's from this vertical asymptote to 0, it's increasing. And then from 0 to 3/2, it's decreasing. So it's gonna look like this. Now is it concave up or concave down? Well, from -3/2 to 3/2, it's concave down. So it's gonna look like this. And there you go. There you drew your function g at x.